Okay, rainbows. I'm passionate about rainbows because I'm fascinated by light and color. So here's a drawing I did back in 1995 explaining all the basic facts about rainbows. That's the way I used to crystallize knowledge back then, was to draw on paper the fundamentals from previous research. Drawing and writing was a way to explain back to myself everything I had so far understood. So I tried to cram as much information onto one sheet of paper. So let's take a closer look at all this. So here's the basic workings of a rainbow, or I should say the primary and secondary bows, or double rainbow. The bows always form part of a circle centered on the antisolar point, which is always the head of an observer's shadow. So there you can see the observer just near the bottom of the screen, and the sunlight is coming in at a certain angle, and the rainbow is projected, or is perceived, directly encircling the antisolar point. And the angle of the bows relative to the incident sunlight would be 42 degrees for the primary bow and 51 degrees for the secondary bow. Now let's take a look at why these angles exist. So, in primary bows, light refracts while entering the edge of drops, reflects off the inside back surface, and then finally refracts again while leaving the drops other side. And you can see there that the angle is 42 degrees approximately. Now, what is refraction? Well, refraction of light is it bends when it's going from one medium to another. So you can see the light going into the edge of the raindrop, and it's bent. And as it's refracted, because different colors refract more than others, the white light is split up into the spectral colors, it's dispersed into colors. And then it's reflected off the back of the droplet, inside back of the droplet, and then it's bent once more as it exits the droplet. It's refracted again. So that's what creates the primary bow. The secondary bows, as I've drawn here, light in dimmer secondary bows reflects twice inside the drops. Thus, the refracted spectrum has colors in a reversed order to that of the brighter primary bows. I can't even talk. So you can see, if you look closely at that diagram, the sunlight's coming in, it's refracted, it's reflecting twice off the inside of the raindrop, and as it comes out, it's refracted again, and the angle is approximately 51 degrees. And the order of the spectrum is opposite to that which in the primary bow. So what we would see, if you can see a double rainbow, the colors in the weaker secondary bow would be in the opposite sequence to those of the primary bow. So here's a beautiful slide I took many years ago of a double rainbow showing just that. Now, it's easy to make a homemade rainbow using a garden sprinkler or what I call a hose bow, and here's a little video of me experimenting with this. Now you can see that the head of my shadow is always the exact center of the rainbows, even when I move. The rainbows move with me. So, in many ways, what I'm seeing are the unique rainbows that only I would see. If somebody was standing next to me, or a certain distance away, and there was sunlight hitting the spray, they would see a rainbow in a different position, relative to where they are. Now, somebody standing behind the rainbow wouldn't see it. Somebody standing to the side of the rainbow wouldn't see it. You cannot go up to a rainbow, you can't go underneath a rainbow. If you're driving along a highway and you see a rainbow in the east, you're looking out the window, you can't drive past the rainbow and then see it recede into the distance. It's always going to be there in the same position as you drive along, because it's moving with you. So anyway, if you look at this, going back to this slide I took, you can see that the sky, well, you can see that the colors are in the opposite order. The primary bow has the colors going with the red on the outside, and then you've got the secondary bow, which is a bit weaker, with the red on the inside. And notice also that the sky is brighter inside the primary bow and darker between the two bows. This is called Alexandra's dark band. Okay, so here's a rather romanticized drawing I did based on that slide I took of the double rainbow. And I did this drawing in monochrome just to show more clearly Alexandra's dark band, which you can see between the two bows. I think I did that back in 1995 as well. Okay, so what else have I described in this diagram? Let's read this. Two main types. The primary bow is bright and frequently seen. Sometimes the fainter, larger secondary bow appears with it. Supernumerary bows, meaning extra, may rarely appear just inside primary bow. Okay, so what the heck does supernumerary mean? Supernumerary. Fancy word. It just means more than the prescribed number. Additional or extra. So, anyway, the supernumerary bows, they sometimes appear just inside the primary bow, often at the very top of the bow. If we go back to a photo of the hose bow, and if I saturate the colors, and then zoom in on the lower right, you can see that the colors repeat themselves. I can just make out two repetitions. Those are the supernumerary bows. They actually are caused by interference of light rays when the rain droplets are of a uniformly small size. So they don't always appear when there's a rainbow, but they are interesting things to look for. In this video you can see the supernumerary bows just inside the bright bow, not particularly colourful, but they are there. And you can see two or three of them. Okay, so what else can we look at in this diagram? Dog bow. A small rainbow forms in the spray from a dog shaking after a swim. Yes, well, this is what I saw once when my dog was coming out of the lake, and she was shaking herself, and she was just in the right position relative to where I was, that this brief and very colourful miniature rainbow, or part of a rainbow, appeared in the spray. And it was only just a second or so, but I noticed it. So that was interesting. Moonbow. A rare and magical sight is the faint, weakly coloured rainbow sometimes visible due to bright moonlight. Well, I have seen this before, but it was extremely faint, and I couldn't detect any colours at all. So that's the moonbow. Okay. Effect of sun's changing elevation on rainbows. Because rainbows are seen encircling a point directly opposite the sun, a low rainbow, A, is seen when the sun is quite high. With the sun at sunset or sunrise, a high rainbow, B, will be seen, making a full 180-degree semicircle over flat country. Well, that makes sense. So here's an old photograph I took of a high bow, and you can see where the bow intersects the horizon. The angle is almost a right angle. Not quite. And here's a photograph I took of a low rainbow. So the sun would have been fairly high in the sky at the time I took this photograph. Now, as the sun starts to set, its colour often changes from a bright yellowish white to orange and then red, as shown in these slides, which I'm splicing together. When the sun is very low, its light has to travel through a greater depth of the atmosphere before it reaches your eyes. Now, the blue and green parts of the spectrum, which have shorter wavelengths, are more readily scattered than red light. That's why the sky is blue. So as the sun sets, all that's left is the red part of the spectrum. Now, if a rainbow was to occur under these conditions, what would we expect to see? Well, we would expect to see a high rainbow, of course, but also a very red one, because that's the only colour left in the sun's light. All the other colours have been removed by the atmosphere. So these red rainbows do sometimes occur, and they're very spectacular. Here's a photograph I took fairly recently of such a red rainbow when the sun was very low in the sky and very red. And you can see this photograph hasn't been enhanced at all. This is exactly how it appeared. And the rainbow is predominantly red. There's a little bit of green there if you look carefully. And if you look really carefully, you can see the secondary bow, which is pure red. It's very faint. Okay, so here's another diagram I drew back in 1997, showing some more aspects of rainbow science. Okay, a small bow and a large bow link up to form a single bow having one uniform arc. Rainbows may seem to greatly vary in size, from nearby sprinkler bows occupying a few feet of spray to distant natural rainbows arching across wide areas of precipitation. But because an observer always perceives a bow forming anywhere along the surface of an imaginary cone radiating out from the eyes, forming an angle of 42 degrees to the incident rays of sunlight, all rainbows, whether near or far, actually appear the same size. The normal perspective effect of objects shrinking due to distance is perfectly compensated for by the rainbow cone, which expands with distance. So you can see on the left, that the drawing on the left, there's one rainbow, but the right-hand part of it is formed in the spray of a nearby sprinkler. The other part of the rainbow, at the top and on the left, is a natural rainbow, some distance, a greater distance away. But you can see they all add up to one rainbow. And I've written at the top, rainbow and sprinkler bow link here. Colors, however, may not splice exactly if droplets of rain and sprinkler are different sizes. Now if we go to the other drawing I did, from a slightly different angle, you can see what's happening here. You have the observer at the bottom there, and those lines radiating out are what I call the rainbow cone. They're 42 degrees to the incident rays of sunlight, and the further out the rainbow is, the larger the cone. So the sprinkler droplets are nearby, but they're still forming on the surface of the cone. The rainbow further away, where the cone would be bigger, still occupies the same angular size. So that's why the rainbows link together and actually are the same size. It sounds paradoxical, but they are the same. In fact, the rainbow doesn't really have a size. In fact, rainbows don't really exist unless there's somebody there to see them. They only exist because you see it, which is another interesting thing. They move like shadows move. If you walk along, your shadow follows you. If you see a rainbow, the rainbow follows you. But unlike a shadow, somebody standing to the side of you could look over and see your shadow. It could walk up to your shadow. It could stand in your shadow. You can't do that with a rainbow. You can't walk up to a rainbow. You can't stand underneath a rainbow. I've already mentioned this, which is quite interesting. So anyway, that's a little diagram I made to illustrate the rainbow cone, which helps to imagine why rainbows always occupy the same angular size, whether they're near or far, or appear near or far. So that's that. I hope that is illuminating. To learn more about rainbows, there are many books available. I have several books on the subject of rainbows and atmospheric optics. And on the internet there's a vast amount of information about rainbows. This whole website is devoted to rainbows and the science behind them. So if you're interested, there's a lot of information out there available, and it's a fascinating subject. The whole subject of light in nature is extremely fascinating, and I will be making some extra supernumerary videos on other subjects of light in the future. So thanks for watching and take care.